Hello everybody, we will have lecture 24 today and the course is corrosion protection methods. So, today we will start a topic on change in environment and associated change in corrosion rate, and simultaneously we can have the possibilities of corrosion protection. Now, when we talk about change in environment, we talk about the corrosive, okay, or the fluid or the environment, gaseous environment at room temperature, wherever this particular metal or alloy system that is exposed to. For example, when we talk about atmosphere, we expose metals and alloys to humid condition, where you have moisture as well as partial pressure of oxygen, as well as we can have presence of chloride if we talk about the environment near sea coast. So, that is one type of exposure, and then we can also think of exposure of metals and alloys in aqueous solution, or you can talk about exposure of metals and alloys to soil condition. Okay. So, those are the conditions I am talking about, where if you can vary those conditions, you can have a huge variations in corrosion rate, and accordingly we can decide what should be the best suited, or rather I would say the optimally suited process for corrosion protection. So, when we talk about change in environment, again it is not related to the change in metal composition or metal surface condition, those are not part of this change in environment. Okay. So, in fact, change in environment also can include addition of some external agents into that particular corrosive, like inhibitor, addition of inhibitor, but we will have a separate discussion on inhibitor when we talk about a kind of when we discuss more on inhibitor part, and there are several kinds of inhibitors, and these inhibitors what they do, they are added in a very small quantity to the fluid or to the atmosphere where this material is exposed to. Sometimes this inhibitor can also be incorporated in the coating what is put on the metal surface. Okay. So, that inhibitor part will come later, but now coming to this change in environment, we only talk about the conditions like pH, conditions like velocity of the fluid, condition like temperature, condition like addition of oxidizers, or change in concentration of the corrosive. Okay. So, you could see that either we can have the removal of corrosives and then we can have protection, or if we cannot remove the corrosive, then we have to find out a condition where the material would show a very good corrosion protection or corrosion at a lower corrosion rate in that condition. Okay. So, that condition we have to find out what it would be that condition. So, let us begin that. So, we can have two situations when we talk about corrosion protection. In terms of change in environment, one is definitely the removal of corrosive. Okay. For example, we can remove oxygen, we can remove moisture, we can remove NaCl, we can remove Fe+3, which is basically oxidizer, we can remove copper 2+. So, this is another strong oxidizer. So, if we remove all those things, then definitely the corrosion rate, so this would lead to a very low corrosion rate. So, that means this is one way to handle corrosion, one way to go for corrosion protection without any change in the material. Now, there could be another thing. So, these are some of the additions, some of the materials which or the environmental species which would lead to corrosion. Now, there could be a situation like if we can change some of the factors, parameters or factors. What are those parameters factors? So, we can think of temperature, we can think of partial pressure of oxygen, we can think of pH, we can think of velocity. Okay. So, these are the factors which we can change, and accordingly we can see that what would be the condition where we have a low corrosion rate again. So, we have to actually see what condition would lead to low corrosion rate. Okay. So, there could be the third one, which is a possibility. Third one is, we can put it like this, this is first, this is first, this is second, and third one could be addition of inhibitor, okay, which is added in a very small quantity. And interestingly, this inhibitor, most of the times this inhibitor composition is not known. So, when we talk about inhibitor later, we will see the complications associated with inhibitor, and at the same time the kind of advantage it can offer towards corrosion protection. Okay. So, this will be discussed later, but this is basically addition from outside to the fluid or to the environment. Okay. So, this we will talk later, this will be separate discussion, separate broad topic, will be discussed later. Fine. So, we will concentrate on this first two, which is removal of corrosive as well as changing parameters or factors. Now, when we talk about the removal of corrosive, let us see how we can actually go for that corrosion protection if we remove oxygen and H2O. Now, when we talk about removal of H2O, now let us see what it does on metal. Let us say I take iron or steel. Now, in case of steel, in the presence of oxygen and H2O, it can oxidize and it can form Fe2 plus, and oxygen can take up this electron and it converts to for a OH minus. This is the cathodic reaction. This is the anodic reaction, which is corrosion, and this happens in neutral or basic medium. Now, if we try to find out, and this is let us say plain carbon steel, mainly low carbon, let us say mild steel. Okay. So, this when we talk about this mild steel, if we try to plot the corrosion rate with the content of oxygen, then we can see the corrosion rate would look like this. It will be increasing in, it will have increasing trend. It can be like this. This is a kind of trend what can be observed. It can be also like this. Okay. So, this will be ever increasing. Fine. So, if we consider this is a kind of pattern, if we consider, so then these happens, this kind of ever increasing corrosion rate of plain carbon steel with the increase in oxygen content in the presence of H2O, that happens because if we, because of the active behavior of the steel. So, this is active behavior of steel in this environment which is contains oxygen as well as moisture, this particular corrosion pattern can be noticed. Now, for example, in this particular reaction we have H2O. Okay. So, that is basically the aqueous condition to maintain this reaction. Now, if we remove this and let us say this is happening at room temperature, So, if we remove this, so then definitely I do not have moisture to hold this reaction. At room temperature definitely oxidation reaction would not happen. So, if we remove this, definitely I may not have the possibility of this reaction would go down. Okay. So, this particular ever increasing corrosion rate happens when the steel shows active behavior. At the same time, if we look at the constituents, H2 is removed. Okay. If it is removed, then definitely I will not have this cathodic reaction. So, the corrosion rate goes down. So, that is what you would see that when we talk about electronic materials, or let us say even if we consider cold rolled grain oriented steel plate, which is a very useful material for making transformer. Okay. So, this cold rolled grain oriented, here we have silicon of the order of around 3 to 4%. So, there this is useful for transformer core. So, this sheet material, so this is the foremost sheet material in the form of sheet. So, this sheet material, when we talk about the carrying this sheet material or the transportation of this sheet material, we always try to evacuate. When we pack it in a plastic cover, it is evacuated. So, when we do evacuation, a little mechanical pump can be used. It actually removes moisture and oxygen. Now, at the same time, we generally add a silica gel pack. Okay. So, the silica gel pack has the ability to soak moisture. So, that means in both the cases, evacuation as a silica gel pack, it actually removes moisture. So, once we remove moisture, this cathodic reaction is actually getting hindered, and accordingly it does not need that much of electron for this particular cathodic reaction. So, definitely iron would not dissolve much to supply electron. So, the corrosion rate of iron would definitely go down. Okay. So, this is one way of having protection. So, that means removal of moisture at evacuation, a little evacuation using pump. Okay. Of course, after that it has to be airtight. So, that means the sealing should be proper, so that there should not be any leakage, and if the leakage is not there, definitely from outside moisture as well as oxygen would not ingress into the pack, and it will not have any contact with the metal surface. So, that way we can avoid corrosion to a great extent, and it can lead to a protection, nice protection. Now, this is removal of moisture. Now, what happens if we talk about oxygen? Now, if we add oxygen, let us say add it. When we add oxygen, so that means we can term it in terms of increase in partial pressure of oxygen. Okay. So, now what happens if we increase partial pressure of oxygen if the material shows active behavior? This is only possible when active behavior is shown by the material. Now, for that we need to understand mixed potential theory. So, let us see the mixed potential theory for the corrosion of plain carbon steel in atmosphere or in aqueous solution containing dissolved oxygen. Okay. So, this can happen when dissolved oxygen then in aqueous solution. Okay. Now, when we talk about mixed potential theory, let us say this is potential axis in volt, this is log I, log of current density, this is in terms of ampere centimeter square. Now, iron, let us say it has its anodic part and this is my cathodic part. This is I core I 0, which is exchange current density of iron on iron surface, and here oxygen reduction is the controlling reaction for the corrosion of iron, and since it is a neutral condition. So, oxygen reaction, let us say it is happening here. Okay. So, this is I 0 oxygen reduction on iron, and the reduction process is for OH minus, this is E core and this corresponding is I core. Now, PO2 is increasing. So, if we increase PO2, then we can follow up Nernst equation and in this case we are considering reduction potential. So, this is standard reduction potential, and if we consider 25 degree Celsius 1 atmosphere pressure plus RT 4, since there are 4 electrons involved in this reduction process, F is 1 Faraday, Ln concentration of oxidant divided by concentration of reductant. Here the oxidant is O2. So, PO2 divided by OH minus whole 4, and of course, concentration of H2O would also come up, but if we consider H2O to be pure, so then concentration of H2O can be taken as 1. Okay. So, that time this reaction relation would become E naught O2 plus H2 O2 by H2O, sorry, this is not H2O, this is OH minus, because O2 is converting to OH minus plus RT 4F Ln PO2 minus RT 4F Ln OH minus 4. So, this is the equation. Now, if we increase partial pressure of oxygen, that means if we increase the dissolved oxygen in that aqueous solution, so then this value is constant at a particular temperature pressure, and this is the equilibrium potential developed on iron surface for that reduction process, oxygen reduction process. Now, this equilibrium potential would depend on the partial pressure of oxygen and OH concentration. See, if we do not change the OH concentration, OH minus concentration, then if we maintain all the time the neutral medium, then of course, if we increase the PO2, this E O2 OH minus, the equilibrium potential will go up as PO2 goes up. That means, as dissolved oxygen increases, then equilibrium potential would also go up. So, let us say this is the potential E1 for oxygen reduction, and this is the potential EFE equilibrium Okay. Now, if we increase the partial pressure of oxygen, this potential goes up, and here this E1 is nothing but, let us say this is my E1 O2, and this is the second one, which is E2 O2, which is the new reduction potential under equilibrium or non-corroding condition, because if we stay at this point, I would see that the corrosion, that particular reaction is happening at a same rate, whether we consider reduction of oxygen or oxidation of OH minus ion. Okay. So, this part is oxidation part, which is 4 OH minus, it will go to O2 plus 2 H2O plus 4 E. So, this reaction is this particular line, this polarization line, and for this I would request you to go visit the earlier lecture series where these concepts have been explained. Now, this potential would go to the next value, let us say this is the value here. Okay. So, this is the value corresponding to E2 O2, the equilibrium potential for oxygen reduction or oxygen or OH minus ion oxidation. Fine. So, when we have this, if we assume that the I0 does not change, there could be a possibility of change in I0 also, which is the exchange current density of oxygen reduction or oxidation of OH minus on iron surface if we change the concentration. But if we assume that that does not change much, so then it will only lift to a higher value. And at the same time, this rate of reduction process, which is the slope, if that slope also does not change much, so then it will come like this. It will come like this. So, this is my new reduction line or polarization line corresponding to I cathodic, and this line is I anodic, we call it IA, this is called as IC. Now, previously when the oxygen partial pressure was maintained in such a way that equilibrium potential was E1O2, that means this value, that time the corrosion rate was at this point, which corresponds to this value. Now, once we have increased the dissolved oxygen, the partial pressure of oxygen goes up and correspondingly equilibrium potential moves to the new value, which is E2 oxygen. Then the new corrosion rate point would be, as per mixed potential, would be at this point. So, the new E core would be at this location, but I core would be at this location when oxygen partial pressure goes up. So, you could see that the corrosion rate has moved from this to this. So, there is an increase, and this is to be remembered, or this is to be noticed, that this is in log scale. So, there is a little change in the value, it actually indicates a good amount of change in the corrosion rate, because there could be a change in the orders of magnitude. Okay. So, we could see that if we increase oxygen partial pressure, definitely the corrosion rate of iron would increase, and at the same time if you see the iron anodic part, it is ever increasing. Okay. So, that means it is showing active behavior all the time. Now, hence if we reduce PO2, if it is reduced from, let us say, this point, from this reference, so then we can have another reduction potential which can be found out from the Nernst equation. So, this value, if we consider this value, so this value, let us say it is at this location. let us say at this location. This is E3O2, and we will have two arms. One is anodic arm, one is cathodic arm for the oxygen reaction process. So, if we only talk about the cathodic arm, because that goes to the that follows the mixed potential theory. So, it comes and cuts it here. Now, since the oxygen partial pressure has reduced in comparison to the oxygen partial pressure was what was maintained corresponding to the equilibrium potential E1O2. So, since it has reduced, the potential corresponding to that equilibrium potential has also reduced. And again, if we follow the mixed potential theory, so that means which will appear, which will reach to this point, the new I core when PO2 is reduced, and we could see that this corresponds to new E core. Okay. Now, there I could see that the corrosion rate has reduced to a great extent. So, that definitely indicates that we can have a low corrosion rate as we decrease the concentration or the content of oxygen, or in other way if we reduce the dissolved oxygen, or if we can reduce the partial pressure of oxygen. Okay. So, that means if we remove moisture, if we remove oxygen, definitely we have the benefit of having a better corrosion protection. And we could see, even if we consider the electronic packaging, electronic packets, if we order something from online shopping, going to online shop and then purchase some electronic item, you will see that the pack is coming in such a fashion that it is airtight. Okay. So, that means you have to puncture. If you puncture, you will see a blop sound. So, that means it is actually airtight, and at the same time you will see that that particular packet contains a small white color packet. So, that white color packet will, you will see, if you feel it, you will see it is a basically a kind of particulate matter. So, that particulate matter it is nothing but silica gel. So, that silica gel actually absorbs moisture, and at the same time that particular container, that particular pack is actually sometimes evacuated, and if you evacuate, what happens, you can reduce the oxygen content, and sometimes you can add little bit of argon or nitrogen gas, which actually reduces the partial pressure of oxygen further. So, you remove moisture, you remove oxygen, so that for the reduction process, this reduction process, both these reactants you are actually getting rid of. So, this reaction would not happen this way. So, if it does not happen this way, definitely the requirement for electron is not there, hence iron oxidation can be minimized, which is nothing but the corrosion. Okay. So, now we talk about the mixed potential theory all the time. Definitely you please go back to earlier lecture series. Just in short, mixed potential theory, it indicates it based on two principles. One is charge conservation, second is total rate of cathodic current density equal to total rate of anodic current density. Fine. So, if we talk about charge conservation, so it is basically, if we then definitely this relation would come up, and of course, third one is a mixed potential will be reached where these two conditions will be maintained. So, this is in brief about mixed potential theory, but you can have a detailed explanation of mixed potential theory in our earlier lecture series. So, now you could see that the removal of oxygen or moisture can actually reduce corrosion rate for active metals. Fine. So, now let us talk about presence of chloride. Okay. So, presence of chloride or removal of chloride, mainly if we talk about NaCl. So, NaCl can lead to several corrosion forms. In fact, it actually affects the passivity. It can affect crevice, it can affect pitting, it can also affect intergranular corrosion. Fine. So, now for example, if we talk about the major reason for crevice attack or pitting attack is nothing but hydrolysis of metal chloride. Okay. So, what it happens? So, let us say metal chloride is forming, it hydrolyzes, it forms metal hydroxide plus HCl. So, now if you see this hydrolysis reaction happens within crevice or pitting or pits. Now, this chloride source is nothing but the presence of NaCl, and it actually leads to H plus ion concentration, which can go up due to this hydrolysis reaction. Okay. So, now you see H plus ion concentration gradually goes up due to hydrolysis, and if we increase the H plus ion concentration, so it actually what it does, pH reduces and it actually goes to active dissolution, since this decrease in pH leads to corrosion zone in pore bay diagram. Okay. So, it actually takes the metal to the corrosion zone. Now, as we know that the corrosion zone means, if we talk about pore bay diagram of nickel, let us say, so the diagram looks like this. So, where you have this is nickel plus plus, this is nickel, this is nickel OH hole 2. So, this zone is passive zone, this is corrosion zone, this is immune zone. Fine. Now, let us say if I am here, pH is let us say around close to 11. Now, this is pH axis and this is potential axis and this is pore bay diagram of nickel. So, now if we increase the hydrogen ion concentration, so this point can move this way as we reduce the pH, and you could see that initially it was in the passive zone, now it has come to active zone. So, which is the corrosion zone. So, that is what I mean, increase in H plus concentration, decrease in pH, and definitely it actually leads to active dissolution and rapid dissolution in the crevice or in the pit would go on, and this becomes autocatalytic. And now you must be wondering why this MCl, which is metal chloride, forms. So, initially we have metal dissolution at all segment. If we talk about in brief, let us say a crevice portion. So, let us say this is my crevice. Now, initially all places metal dissolution as well as oxygen reduction can happen. Okay. and then after some time there would be depletion of, if we talk about different steps, first so these two reactions happen on all surfaces it happens. Now, this crevice is a narrow portion which allows solution ingress, at the same time it does not allow any movement or it maintains stagnancy. Okay. So, these two conditions are critical for crevice corrosion to form, and this opening I am talking about, this opening is narrow enough to maintain stagnancy and wide enough to allow solution ingress. So, then when we have this, gradually the oxygen in the crevice zone, in this zone will deplete, but all around the oxygen concentration will be maintained, and this is NaCl solution or freely aerated NaCl solution. What we talk about freely aeration, when the solution is exposed to open atmosphere or the seawater is exposed to open atmosphere. So, oxygen concentration in the crevice would decrease, and that would allow this portion to become anode preferentially, and the rest of the portions are cathode. So, then depletion of oxygen in crevice. Next step is crevice becomes anode. So, large cathode area outside crevice, and small anode area inside crevice. The next is, since crevice portion becomes preferentially anode, lot of metal ion would dissolve there. So, that means there would be excessive positive ion concentration inside the crevice. So, excessive metal ion content. So, that means the crevice is becoming positively charged. Because of the rapid dissolution of metal there. Now, since it is positively charged, so that means that the system would like to maintain electroneutrality. So, then definitely from outside negative charge must come into the crevice to balance out this metal ion. So, then there will be competition between OH minus and chlorine ion, and the chlorine ion would like to preferentially go there because it has a higher mobility. So, chlorine ion moves inside crevice, okay, and then metal chloride formation, and then hydrolysis, H plus ion increase, which led to pH decrease, and then finally metal goes to active corrosion condition. So, these are the steps for crevice attack. Now, you could see that the presence of sodium chloride can lead to such a dangerous localized corrosion mode. So, that means if we remove chloride, definitely we can have a very good corrosion protection, because that chloride related influence would not be there. Now, as we see that we have to remove chloride ion to get a very good protection. So, that means again what we talked about, that if we remove corrosive or some of the chemicals which help in corrosion, okay, if we remove, then definitely we can have good amount of protection. So, we will talk on this removal of corrosives more in our subsequent lecture. Till then, thank you.